So these handouts, depending on how much paper you want to use, this one here, all the questions are on one sheet, but there's really not a lot of room to write. This one over here, so handout versus worksheet. WS stands for worksheet. That's my notation. Gives you a little more room, and it goes on to 2 pages. I do this for my other classes where you really need 1 page per problem. So so that there you're looking at the difference between like 6 pages and 1 page, if I put them all on one or not. So yeah, you should have that, and then I'll upload the video when we're done. Oh, formula sheet for Mod 3 quiz. It's right here. Yeah, this is basically the same formula as you'll be using for test number 1. So it says test number 1 on the top. That's because this is the same formula sheet you'll be using. And since we're here, yesterday I mentioned, let's see, I mentioned the test material was in this folder. The test is not here yet. It will show up. But I did update the review packet with the correct date, February 18th. So if you'd like to print this out with the correct date on it, it's there. How many pages is this? This is 5 pages. And we'll go through these probably starting Monday, depending on how far we get today. And then, yeah, so I would have this printed out for Monday, or at least however you're taking notes, right? I'll probably do some multiple choice question, sort of like a quiz bowl thing, not, just like polls. I'll have to set them up over the weekend, but I won't do them for necessarily all the problems, just some of them. All right. And then the formula sheet is also relinked here. So this is the same formula sheet as is in the Mod 3 folder. So you should have this printed out for your test, which again is 2 weeks away. So you have time on that. All right, let's, any more questions about anything before we get started? Okay, let's see, let me check the chat, nothing in the chat. Okay, so let's see. Oh, I flipped my notes to the wrong page. So last time we talked about the 3 variable equation, then we talked about proportionality, and we left off with, oh, was there any question on the last page of the math packet, page 29, which is the, pretty much this, the directly and inversely proportional? Okay, so that was that. And then again, the end of the math packet, or the back of the math packet, has your conversion factors and your reference table. And then there's also so this is from the math packet, it's double-sided. The one for the test, it's on one side, so everything's on one front. Notice the equation here. Oh, you know what? Let me use the PDF, because that's this is what you're going to see on the test. That's not it. I might as well refer to the one you're going to see on the test, because all right, so notice down here, right, I put for if you want to use the triangle method, I put the density formula in at the bottom here with the triangle, right? So you can see this is what the formula looks like, and you can replace this with any formula, right? But know how to use the triangle, right? You just cover up. You want V, you got M over rho. You got M, you got rho times V. But we're going to do examples.
Uh-oh.
This is Mod 2 or Mod 3, page 2, I believe. Sorry guys, my notes, I'm doing my notes a little bit differently this semester, thinking it's going to help me keep more organized, which In some way it is, in some ways it's not. So this is mod 3, and let's talk about, I can get to my notes. We're going to talk about density. The density. All right, so density, first off, is a property of matter. And it's basically, yeah, basically it's the compactness, right? So if you go out right now and, well, maybe depends on where you are, the compactness of matter, right? So if you go outside and you find some snow, it's going to be, you're going to pick it up. It's going to sort of maybe crumble apart. But then you take that snow and you put it between your hands and you press it together, right? What are you doing? You're compacting it, right? You're making it. You're taking that fluffy amount of snow in your hand. You're pressing it together and making it nice and compact, right? A nice compact snowball. And what are you doing? You're taking and you're basically making it denser. You're taking the same amount of material and you're putting it into a smaller volume. So this is how much matter or mass is in a given volume. So let's look at the equation for density again. We've got rho equals m over v. This is supposed to be a capital V. I don't know if you can really, there's certain letters it's just so hard to tell if they're capital or not. Let me write out the definitions of each of these. So rho is, so this is RHO, it's the Greek letter rho, is equal to density. And the units on this are grams per cubic centimeter, typically. You'll see these in your textbook. But it can really be any mass per unit volume, right? It could be kilograms per cubic meter or, pounds per cubic foot. We're going to use in this class pretty much grams per cubic centimeter. And the mass here, M, is mass. And those units are grams, and V is volume in this equation. As you may have noticed earlier, some equations use redundant symbols. Like when we get to motion, we're going to use little v for velocity, but it's going to be, you're going to have to keep track of what's the context of the equation. Right, because V is volume here. V could be, velocity or something else, depending on what we're doing. All right, so let's look at the density of aluminum. If I go to the table here, there's a table from your textbook, table 1.3. The density of aluminum is 2.70 grams per cubic centimeter. These are common substances, right? Mercury, is it? All right, so let's write this down. 2.7 grams per cubic centimeter. And this is from table 1.3. So what does this mean? This means that there is a mass of 2.70 grams of aluminum is in a 1.0 cubic centimeter volume. Right. 2.7 grams per cubic centimeter volume. So if someone were to ask you for a volume of 2.0 cubic centimeters of aluminum, what is the mass? Right? You could take your equation
5.0 or 5.4.
Did you say 5.84?
Sure.
5.4 is, well, let's walk through this because I just want to make sure everyone's getting it. Right? Here's your equation. Rho equals mass over volume. I'm just going to write that down. I'll move my notes up in a minute. Actually, let me. So we know. Oh my God, my writing is. You guys right now are probably wishing you had a packet for this. You're like, oh my God, notes are all over the place. We know what? We know volume is 2.0 cubic centimeters. And we know the density of aluminum is 2.70 grams per cubic centimeter. Right? Now we just have to rearrange this equation to find M. And again, if you look up in your, use your triangle, right? M is rho times V, or you just use algebra and you say M is rho times V, which is equal to 2.70 grams per cubic centimeter times 2.0 centimeters cubed, right? And where's my red canceling pen? We can see that we multiply, we're going to get, well, we'll get the 5.4. And then the units, the cubic centimeters are going to cancel, right? Because we've got, this is grams divided by cubic centimeter. This is times cubic centimeter on top, right? So we're left with 5.4 grams. So the mass equals 5. And so this is where you check your significant figures. I've got 2 here, 5.4 grams. Right? So just taking the density, multiplying it by the volume, and getting the mass of aluminum contained within 2 cubic centimeters of volume. And let's see. So this is these are some average densities. Let me move this up. Start a new page. So that table 1.3 is densities of common materials. Let's talk about something called average density, because you'll hear that average density. The average density, this takes into account all material in an object, including air. So, for example, Well, you know what? Before I give you this example, let me go back to the snowball, right? You pick up a bunch of fluffy white snow and you're holding it in your hand and you've got this bunch of snow and it's a combination of, snowflakes and air, right? So you're the same amount of mass of snow is in your hand as when you press it into a snowball. It's just that it includes a bunch of air. So the density, right, is lower when you first scoop it up, and then you start pressing it together. And what are you doing? You're pushing together the snow flakes, and you're basically pushing out the air, right? So you've got a smaller volume that only contains snow. I mean, you're going to still have some air in there. But another example here is a boat. Has a lower average density, than water. So in a fluid, such as air or water, objects with a greater density than the fluid sink. Objects with lower density float.
Like submarines.
Right, right. So a submarine, right, is going to take on, a submarine is basically this hollow steel death trap, right? Hollow steel vessel. And what do? They have it's got a certain amount of displacement, and normally it floats just above the water level. And, it's got these tanks in there that they can fill up with water and take on water and basically, displace some of that air that's helping keeping it buoyant, and then it sort of sinks, right? And modern submarines are probably very good at controlling this volume level, probably with systems that, in the old days, I think they just used to have a manual pump and blowout. But that requires energy to pump. You got to displacing the air doesn't require as much energy as now. You got to displace the water to be able to rise again. So you need to have pressurized air somehow. The other thing is, if you've ever taken, maybe some of you know, there's a way to do body fat measurements where they take your weight in air, and they also take your weight in water, but they also take your volume displacement in water. And that's because they make an assumption about the human body. They know the density of fat on average, and they know the density, again, on average of, the rest of your tissues. So based on the difference in your weight, both in air and, in air and in water, and also your volume displacement, they can figure out approximately your body fat because you're working with density. It's a little more complicated than just a boat, but that same principle is used in what is it called, body composition measurements. So if you're into like bodybuilding or something, or I don't know, someone that is, right? They probably have their body fat measured. they use calipers as well, but probably the gold standard is basically water displacement. They have machines now that do volumetric air displacement as well. Okay, so that's this is density and average density. Now, there's some factors in the environment that can affect density, right? So let's talk about that. Environmental factors. Factors that affect density. Let me just rewrite the formula here. Okay, so this goes back to proportionality. Let me just draw a little line here so it doesn't, looks like there's a break. If you have something sitting outside, there's going to be some environmental factors that affect it. Now, mass is typically constant, right? So we're going to rewrite this as a proportionality statement. This is going to be holding M constant, holding mass constant. You can write density is inversely proportional to volume. Now, what typically happens to a material as the temperature increases? What happens to the volume of that material? Anyone know?
When the temperature increases,
Yeah.
doesn't it expand?
Yes, it expands. So one classic example of this is railroad tracks. So if you make railroad tracks too long, or if you make the track itself too long, you don't leave enough room at the end for expansion. And I've actually seen this happen with asphalt roads, where they'll start getting buckles in them because they've been laid down during the wrong temperature of the year, or they've been laid down as one continuous strip, and there's not enough room for expansion or contraction. So a railroad tie, right, will be out there, and maybe you laid it down in spring or fall, and then in the middle of a hot summer, it can expand. And if there's not enough gaps at each end for expansion, that railroad tie is going to reach, it's going to bump up against the other, or not the railroad tie, the railroad track is going to bump up against the next railroad track, right, the steel, and it's going to have no place to go, so it's going to start buckling outwards, right? And that's what used to, there's been train derailments because of temperature change. So you have the same amount of mass and the volume increases. So let's write this out. As temperature, I'm going to abbreviate, temperature increases, right? Materials usually expand, causing an increase in volume. And what's this going to do to density? If volume increases and density is inversely proportional to volume, what's going to happen to density?
Goes up.
I'm sorry, I didn't hear.
Decrease.
Let me turn my volume up. I thought I heard some decreases. It is decrease. Increase in volume and a decrease in density. So let's think about this, right? You're holding the mass constant, right? So you take the same amount of mass and now you've increased the volume, right? So you've made it bigger. You're taking that mass and you're somehow expanding it outwards. In this case with temperature. And so the volume is increasing, right? Your density is mass per unit volume, right? How much mass you have in a certain amount of volume. Well, you have the same amount of mass, but now it's in a much bigger volume. Well, it's in a bigger volume, your density goes down. And the same thing happens in the other direction, right? A lot of times the temperature or objects will shrink as temperature decreases. So if volume decreases, right, density will increase because now you've got the same amount of mass. So think about the snowball for that situation, right? As the volume decreases, right, as you compress that snow together, I think that one's a little more intuitive because you can go sort of picture compressing something together. Or just think of I used to have one somewhere, one of those stress balls. Where's my stress ball? Hold on one second. Might be in here, maybe. No, that's a cross ball. Oh, I found it. Stress ball. All right, so here's a stress ball, right? If I squeeze it, I'm decreasing the volume, right? But the same amount of mass is in here. So volume decreased, density went up. Now I'm releasing it, right? The same amount of mass, but my volume is bigger, so now the density is now lower. And remember, this thing's got a lot of air. If you were to cut this, it's kind of a foamy, right? You've seen the inside of this. It's kind of a foamy, it's a foam. Foamy foam. So that's what you're doing, displacing. And this has got an average density because of that, the foam that's got air as a combination of whatever the foam plastic is. All right, so B. And again, B is a little more intuitive because this is pressure now, and we just kind of went through a bunch of examples where we're, applying pressure to something like the foam ball. So typically, an increase in pressure decreases volume. Right? This is my stress ball. I'm applying pressure to it. You can't actually see what's happening. I'm applying pressure to it. I'm decreasing its volume, right? Take the snowball, I apply pressure to it, I'm decreasing, or the snow, and I make it into a ball and decreasing its volume. An increase in pressure decreases volume and causes density to increase. Well, yeah, we can see it right up here on the proportion. So again, volume, I'll just write it out. As volume increases, right? You're taking and dividing by a bigger number, so this becomes a smaller number. Density decreases, right? If you hold volume constant, obviously your density is the same. And as mass increases, oh, well, we won't talk about mass, but you can write the same proportionality for density and mass. Well, not the same, but a different proportionality. But this is for environmental factors. So typically environmental factors are influencing density or volume. And that's how they affect density. Now, you could have a factor like rust, right? And that could cause a change in the mass, but typically it changes the volume as well. And that's something that's a little more complicated, but we're focused typically on volume. Temperature and pressure change the volume, and that changes the density. The last thing I want to talk about for density is water. What time is it? Oh, 11. Yeah, we got time. Let's talk about the density of water. All right. So water is unique because it's the only common substance for which the solid state is less dense than the liquid state. And this is so common around us that I think it confuses people's concept of the relationship between mass, volume, and density. Because water is, well, I guess it confuses the concept of environmental factors. Water is one of those few substances, and really the only common substance. I'm trying to remember which other substances do this, and I can't, off the top of my head, I can't remember. Where the solid state is less dense than the liquid state, right? Most materials, when they're solid, they're more dense than when they're a liquid. Oops. So let's start a new bullet here. When water is cooled, it contracts until it reaches 4 degrees C. So liquid water does actually get denser as it cools. And then it hits 4 degrees C. Then it begins to expand and this expansion decreases its density. So let me move this down a little bit. Right, so for a given mass of water, as it cools down, this volume actually gets smaller. So the density is going to increase. However, as soon as you hit 4 degrees C, that's the turning point, and that volume starts to increase again. So the density starts decreasing. So why does this happen? Well, below 4 degrees C, water begins to form a crystal structure. I guess let me put a comma here, of ice. So this crystal structure takes up more space than free, we'll say free molecules of water. So it expands. So finally, at 0 degrees C or 32 degrees Fahrenheit, the freezing point of water, the crystal structure finishes forming as ice is formed. Ice is formed. There's no real good way to say that. I mean, obviously it's forming ice as it forms this crystal structure, right? So this is what's happening as ice is formed. Normally the molecules of water can fit closer to each other than its crystal structure. Again, this is not the normal case for most materials. For most materials, when they start cooling down, you know, just like water in the liquid phase, as molecules start as you cool a material, we're going to talk about this in the context of temperature in a later module. But think about it, right? You're in a say you're in a room with a bunch of high energy people that are moving around, right? You're gonna you're gonna want to expand out as a crowd, right? Because these people are annoying. They're just bumping into you, right? But if you're in a room where people are like standing very still and you can sort of gather closer together, right? That's what's happening with temperature. You know, higher temperatures of substances, the molecules are moving around really quick, right? They're bouncing off of each other. They're pushing each other apart. They're really annoying. And then as you start to drop the temperature, right, they slow down. So they're not bumping into each other as hard. They're able to, you know, stay closer together within a smaller volume. So that's why you get the contraction and expansion. However, and then again, for most substances, you get into that crystal structure, it becomes even tighter. But for water, the crystal structure of water actually allows it to take up more space than it does as liquid water. Yeah, so that's why water formed. And this is, I mean, this property of water is critical for life on the planet. Because if ice did not float, right, you'd basically wind up having ponds that, you know, the ice would sort of sink and take up all the water below, you know, in the deep parts of the ocean or the ponds, right? I mean, oceans are, well, they're salt water, so you really need some cold temperatures. But fresh water, right? The fresh water would freeze and the ice wouldn't stay on top; it would sink to the bottom, and the whole pond would be pretty much filled with ice. And if you've taken a bio class, you probably have heard this about how, in the winter, a lot of fish and other pond life, it stays in the bottom of the pond because it's still liquid down there, right? It's not frozen solid, and they can survive even if they're sort of just hibernating. They don't freeze. All right. So that's density. I have here some packet or problems to work through. Are there any questions about the concept before we start working on some problems? Oh, 11:45. I have time to get through these, or well, not all of them, but some of them. All right, what's the density of iron if 5 cubic centimeters has a mass of 39.5 grams? So the first thing we're going to do is we're going to write down our density formula. Oh, and look, we don't even have to do any rearranging, right? We looked it up on our sheet. It's the form we need. We need to know the density, right? M is given is 39.5 grams. V is 5.0 cubic centimeters. So we're given all the information we got. We can plug that in. We've got density is 39.5 grams divided by 5.0 cubic centimeters. And what do we get? We get, well, I don't actually know what the calculator is going to give me. 39.5. Let me put my calculator here. Figure the whole 39.5 divided by 5. Oh, it does give you exactly 7.9. Okay. So I get 7.9. And I look at my significant figures and I say, okay, I've got 3 significant figures here, 2 significant figures here. My overall number of significant figures is 2 from the rules of division or multiplication. You go with the least number of significant figures. So I've got 7.9 grams per cubic centimeter.
So what page is that in the packet? I don't think I have that one.
This is not in the math packet. This is a separate handout that I mentioned.
It's in the module 3.
Oh, okay.
Yeah, it's in module 3. This one right here, there's some handouts up here.
All right.
Yeah, and again, I normally write these out, but my handwriting is, you've seen it. It's it's not pretty. So I started typing them up. I don't have everything typed up, but I'm working my way through the class. All right. Now, it's a trade-off, because if you type too much stuff up, like the notes, right? I want you to write the notes. And if I just type it up, you're less likely to actually take the notes and write them. And even if I go through them, I'm not going to go through them as slowly as I would need to do to have you write them and keep up, right? So it's there's something useful about writing the notes where I'm writing them and you're probably not writing that much slower than me. Also, there's a learning advantage to actually writing the material down. You're more likely to remember it and recall it when you're writing it down yourself. All right, we can do this next one real quick, and then we'll stop here. What's the mass of a 10 cubic centimeter cube of copper? Okay, so now we've got the density equation. And we want to look at this. We want to find the mass. So we're going to find the mass, and that's mass is density times volume. So let me rewrite this. And what do we have? We have V equals 10.0 centimeters cubed. Well, we need rho. Oh, you know what? We have a table of common or densities of common substances. And copper is one of those substances. So we can look up the density of copper. This is an 8.96 grams per cubic centimeter. So I'm going to write rho is 8.96. And this is from, I'll use red here, table 1.3. So now we just plug this in. 8.96 grams per cubic centimeter times a volume of 10.0 cubic centimeters. Our cubic centimeters cancel. And we're left with a mass of 89.6 grams. And notice my significant figures here, in both cases, they're 3. So I just reported it out to 3. So that's our mass. This is using the density formula and also the tables. And I mean, feel free to work ahead, and then I'll go through these on Monday. So I'll just do the rest of these. Example 3 and 4 are fairly straightforward. Oh, and so is 5. Number 6 is more of a problem solving. So you have to do some thinking about that. So we'll work through those on Monday. All right. Any other questions before you go? Or?
No, I'm good.